Hi, hello. I'm Xiao. I'm a core developer at Nervos CKB. We are building a new layer 1 blockchain solution. I believe we have some novel ideas, so if you want to learn more about Nervos CKB, please come to me after this talk. We can share more. But unfortunately, this talk is not about CKB itself. This talk is focused on the CKB VM, which is the brand new VM layer we're building here. So today's talk is going to be a two-part. First part is a retrospective on how we can design a better VM for blockchains. The second part is the main. It is more closely aligned to our today's topic here. How we can build performant VM in Rust. We all love Rust. We all enjoy writing code in Rust, but as we're going to show here, writing performant Rust codes also have some hiccups you need to be careful about. So let's begin with the first part, how we can design a new virtual machine. Okay, so we all know that a blockchain virtual machine has certain properties that you need to meet. And two important properties that here, the first one is determinism. A virtual machine for a blockchain should produce the same result no matter where you run it, no matter where you run it, when you run it, and whatever machine you're running on. Two VM instances must produce the same results, even the same input. There's no non-determinism allowed in a virtual machine for blockchains. The second part is security. A virtual machine should not just, is it going to be better if we just don't use the mic or something? Okay.
I'm going to turn the mic down.
Okay. So security is the second thing. We must ensure that the VM is secure at most. It shouldn't steal anything from your virtual machine. It shouldn't steal anything from your main computer. Your virtual machine should be safe. The smart contract running in the virtual machine should also be safe. If your computer has other sensitive information, the VM should not be able to tamper that with. Also, the VM has to be able to secure enough. So when the bad program runs on the virtual machine, the most thing you can do is just invalidation and execution. There's no other thing it should damage. But these things are only requirements for a blockchain VM. We're also thinking about how we can make a blockchain virtual machine better. We did a retrospective, we did some thoughts here. We believe there are three main properties. The first thing is that a blockchain virtual machine should be flexible enough to support any case. And yet it also should be simple enough to reduce the attack surface. We can have a very complicated virtual machine that can solve any case, but a complicated one means more attack surface. More attack surface means it may not be secure enough, and it's also so hard to do a security audit to make sure our VM is secure enough. Also, the flexible part means that as much as we can, although we can mostly use hard forks or soft forks, a different kind of upgrades environment to upgrade your VM. One thing I think we should be sure is that the program, the smart contract you write today on the VM should also be valid tomorrow. It should be also valid that a year from now. I think it should actually be valid forever. This is the only way we can make sure that the developers' efforts won't go in vain. So this is the first part. The second part is that we believe a blockchain virtual machine should have industry support. Although we can design a brand new virtual machine that runs everywhere, but the problem is that if everything you build is start from scratch, you have to write your own tool chain. Everything has to be built by your team. If there's no industry support, you're on your own. And it really depends on how many resources you can get to make sure that virtual machine is good enough. The third part is that we should have a reasonable future-proof runtime cost model. We have a smart contract running on a virtual machine. We must be sure that a smart contract should be associated with certain amount of cost. If the smart contract does more work, it should cost more. If the virtual machine does less work, it should cost less. And this thing has to be future-proof because we don't know 10 years from now what CPU we will have, what computer architecture we will have, and on what platform we should run this smart contract. What we cannot have is like this smart contract costs like 10 today, but costs only 5 like 10 years from now. That's gonna bring catastrophic to our blockchain system. With those goals, we search, and we believe we found the answer in RISC-V. So RISC-V is an open and frozen instruction set architecture. It's originally designed by a bunch of by a group of professors at Berkeley. Their goal is like they want to revise what the computer architecture has advanced in the past 50 years, and they want to start from scratch and build a new instruction set for the next 50 years. So one question they ask is like, if we forget about all the burdens we have in the instruction set and design something that works for the future and works better, how this thing is going to be? And their answer is RISC-V. So our CKB VM is actually a standard compliant RISC-V instruction set software implementation. We didn't introduce any other variables. We just built a standard RISC-V compatible software CPU. And the one thing I want to mention is that our goal is the 3 goals before. We didn't aim to look for a hardware-based instruction set. This is because we find the best properties in RISC-V. Let me show you why we think RISC-V is better. The first thing is that RISC-V has real industry support. We have all kinds of hardware companies building RISC-V CPUs. Western Digital has announced that all the hard drives in the future will be based on RISC-V. The main control chip in Western Digital will be converted to using the RISC-V instruction set. So I would say it's very likely in the next 10 years, any hard drive you buy from Western Digital will have a RISC-V CPU in it. Also, right now, if you have a latest NVIDIA GPU, it's very likely it already includes a RISC-V chip on it. They use RISC-V to build their control chip. And also there's a whole bunch of other companies, they're all building RISC-V CPUs, but this is only the hardware side of the world. On the software side of the world, RISC-V has already been supported by upstream Linux. It has also been supported by the GNU toolchain. So these things are all upstream, they are officially supported. If you pull down GCC 9 and build it with RISC-V support, you should be able to write a C program and compile it to RISC-V. Recently, LVM also announced that starting from LVM 9, RISC-V is also going to be the official support instruction set. It means any RISC-V code in the future will be supported by the official. Any LVM standard distribution built in the future will be able to generate RISC-V code. Also, there's a recent article written by the Debian group showing their progress in their RISC-V core. There's some hiccup they run too, but things are progressing. Soon we may have the full Debian running on RISC-V chips. And the official Go implementation also has rapid development in the RISC-V world. I believe as of now, you can already compile certain Go programming to RISC-V and run on the RISC-V CPU. The same thing happens for Rust. Rust also has growing RISC-V support. This thing is a little bit immature right now, but I think with time, this thing is going to get more mature, and soon our Rust program will also be able to run on RISC-V chips. So the conclusion we can get here is that the whole software industry is really embracing RISC-V, both from a software and a hardware point of view. So besides industry support, the other thing I want to show is that RISC-V instruction set is very minimal. Actually, the complete core RISC-V instruction set can fit into 2 single pieces of paper. And instead of just listing the instruction set here, you can see that each instruction has an associated memo there. And they even have space to include things like calling conventions and encoding formats. So you can see the space is really sparse, but they really do cover everything here. That shows that, I believe that can show us that RISC-V is really a minimal instruction set. And actually, if you look at our CKB VM, we don't even need everything here. So I just mark out the part we don't need. You can see that we have plenty of space. There's only very minimal thing we need to support to build a RISC-V CPU in RISC-V, in CKB VM. And the result is, if you look at CKB VM right now, we only need to implement like 103 instructions. This is smaller than the instruction in EVM. This is also smaller than the instructions in Bitcoin script. This is way smaller than the instruction set you have in an x86 CPU. But even though RISC-V is minimal, it's also flexible. What I tend to like to see is that we're not embedding a virtual machine in our CKB blockchain. We're actually embedding a real minimal computer in our CKB chain. The result is that we are more than adequate to support existing use case. So you can issue new ERC20 tokens on CKB. You can do Responseware. You can do whatever existing blockchains can do. But as I'm going to show later, with CKB VM, we can also enable new use cases. The first use case is like this. Today you can see that most blockchains use SECP256K1 as the signature verification algorithm. There's also new development in signature verification like Xiao, like BLS. But the problem is, today we may have this existing signature verification algorithm, but what about 5 years from now? What about 10 years from now? When new signature verifications came out, how easy is it going to be for our blockchain to support this? I believe we can also see that Bitcoin teams spend a huge amount of effort just to support Schnorr signature verification in their chain. But what if Schnorr becomes something old? What if newer and better things than Schnorr comes out? So our solution here is that instead of embedding a signature verification algorithm in CKB, we just take the CKB verification algorithm code, compile that to RISC-V, and we just embed a RISC-V binary code onto our chain. The result is we're not bound to any single verification algorithm. We're free to support anything you want. If you don't like our official supported one, don't worry, you can just build Schnorr and deploy on CKB chain, then you can use Schnorr to do signature verification. And this means there's no need to wait for any pre-compiles. If you want something, you can deploy it right now. There's no need to wait for the official team or to persuade the official team to support anything. And also, one beautiful part of CKB is that your deploy contract is treated exactly the same way as our official ones. Our official included signature is just there because we put it there. It doesn't have any special privilege. Every smart contract running on CKB is really created equal, whether it's created by the official team or created by our community members. One point I keep making is that if your blockchain cannot support Mimble via a smart contract, maybe we shouldn't really call it a programmable blockchain because it is not programmable. The second use case is like, as we can see, as Ethereum 2.0 grows, people are really persuading smart contract developers to move to EVA. They're deprecating this whole Solidity thing, but the thing is, we have all this investment in Solidity. We have all developers using Solidity today. We have a lot of smart contract apps written in Solidity. Are these efforts going to go in vain? If you're working on CKB, the answer is no, because what we can do is that we take an implementation of EVM, or we can also take the implementation of a Bitcoin script VM. We compile the VM directly into RISC-V, then we deploy it on CKB. The result is that you can just run your own EVM code written Solidity or a Bitcoin script on CKB. I think this may not be a very large use case, but it helps us preserve legacy. It helps us preserve all the history we have. It preserves all the efforts we have spent in the existing blockchains. And it also helps make a more vibrant and diversified ecosystem because you are not bound by a single smart contract language. You're free to use your favorite one and any one you want. And that brings to a different use case. You see, all the existing smart contract languages are really designed specially for blockchains. But what if I want to use a general purpose language? For example, JavaScript has a very rich NPM ecosystem. What if the code I want to use is already on NPM? Or what if I want to just write our smart contract in TypeScript? Or even OCaml and compile to JavaScript? Turns out CKB can also support this case because what we can do is that we take a JavaScript implementation, we compile that C-based implementation into RISC-V binary. Then we deploy the binary on CKB. The result is that any JavaScript code can also be running on CKB. This has already been proved. We have real projects supporting this use case. The result is that you don't have to live with something like assembly script or any crappy language. You have the real JavaScript at your fingertip and you can just use that one. And of course, one question might be raised is that if we have this VM on top of the VM solution, the performance might be a little problem. But we believe that it really depends on the use case. You have to measure to see if performance is really a problem. Also, the other way to tackle this problem is that, initially, really, the problem is that we have this JavaScript enabled thing. It's really a 0 versus 1 case. And then as more and more users adopt this JavaScript thing, the community might develop better solution to make this thing more efficient and more performant. And this thing, as this thing grows, things will definitely get faster and faster. And it might not be standing in your way any longer. And the final use case and the one that's most asked when we make a choice to use RISC-V is WebAssembly. Let me first state my conclusion. I believe WebAssembly makes a lot of sense for the web, but it is a questionable choice for blockchains. I'll explain why. There are two parts to this question. The first part is existing WebAssembly have certain quirks that may not make it a very suitable blockchain VM. The second part is that if you look into the future, WebAssembly has all these things that make it a bad choice for a virtual machine, for a blockchain virtual machine. The first case is like to look at some curves. This curve is called heap problem. So all the low-level language, when we use C or C++ or Rust, they all use this certain computer concept called heap. But the problem is that current WebAssembly implementation implements heap in a really poor way. The only way that you can deploy a chunk of VM is to declare it is to predefine a block of memory in your module. When you write a module, you have to know for sure how much memory you want. In some cases, this is going to work, but in some cases, this might not work. And if you look at the literature, look at how everybody is doing things on WebAssembly, what they do is like in JavaScript, they create a array buffer. And they just pass the array buffer from JavaScript into WebAssembly, and then WebAssembly use that array buffer. And when they need to grow the memory, they just enlarge the buffer. This works if we're working for the web, but how are we going to have an array buffer exposed to WebAssembly in the blockchain? This is going to be, I personally believe this is going to be a huge security risk. The second problem is that if you look at the WebAssembly spec, it has a whole section about non-determinism. And they define this non-determinism in a way that makes a lot of sense because they want to optimize for a very secure and very performant system. But the problem is that this non-determinism is going to bring problem for blockchain VM because we stated earlier that the blockchain VM must be deterministic in all cases. And this means all the WebAssembly VM you use in the blockchain today might not actually be a WebAssembly because your VM has to be deterministic. But the official spec for WebAssembly states that it can have certain non-determinism. It means that what you're using is actually a modified WebAssembly. It's not the same WebAssembly. Actually, there's one more important thing here, so let me read this thing out. As WebAssembly gets implemented and tested with multiple languages and multiple architectures, we may revisit some of the design decisions. First point is not relevant, but if you want to see it on the official WebAssembly spec, this is a code. I want to point out the second point here. When different languages have different expectations, then it's unfortunate if WebAssembly measures penalizes one's performance by enforcing determinism. which that language doesn't care about, but which another language may want. This is actually not an assumption. This is actually something that has been proved by fact. You see, if you look at the WebAssembly spec, WebAssembly today has garbage collection implementation. They have garbage collection feature proposed and implemented in some browsers. But the problem is, those garbage collectors are only tuned for one set of application. When people want to use the garbage collection for a different set of applications, they really run into a problem because the garbage collector won't fit their language model. This brings a huge problem of porting Haskell to WebAssembly. There's a real blockchain team working on this problem. They spend a lot of effort to work around this issue. And a bigger problem is the WebAssembly team states that they may even revisit this thing. If you think about WebAssembly, it's actually a software spec. All people need to do to make incompatible changes is just to make all the browser vendors sit in a room, and when all they all agree with each other, they can just ship a new version of WebAssembly which includes incompatible changes. This works for the browser because our browser are all evergreen browser that gets automatically updated. But what about your blockchain? If there's an incompatible change in the WebAssembly spec, how are your blockchains going to support it? Do you need a hard fork to support this, or are you going to only support an older version of WebAssembly which deviates from a then WebAssembly version? This is current curves. Let's look at the future features. If you look at the WebAssembly official site, they have planned a lot of features that's going to implement it next. Some of the notable ones including threads, garbage collections, and on a different slide, there's tail calls, there's multiple value returns, there's import, export, multiple modules. These things are all planned and proposals have been written, and there are real browser vendors implementing each of them. And if you look further, there's also different proposals they're going to add to the WebAssembly spec. This is only some of them, and there's more features, a lot of more features. So that raises a question, is there going to be really an end version, or is there going to be a stop point that we won't add new features to WebAssembly? To me, I'm afraid the question is no. WebAssembly will always be growing because browser is growing. Our web standard is also growing. So it really makes sense for WebAssembly to keep growing because when you only have this thing in the browser and the browser can get automatically updated, WebAssembly can also get updated. But for blockchain VM, as I mentioned earlier, this is a different situation. When WebAssembly gets updated to include a new feature, are you going to keep it up for your blockchain VM? And here with RISC-V, we think we can provide a different solution. We can build a layer that translates your existing WebAssembly code directly into RISC-V. And since RISC-V is an instruction set designed for the hardware, it's frozen and it won't change in the next 50 years. We can be sure there will be real CPUs built using RISC-V, and there's no way you can change them. So this way, if you see a new feature like garbage collection, you can ship the implementation for the garbage collection together with a program, compile that into RISC-V binary, and deploy it on CKB. If there's a new version of the garbage collection, or if there's a different feature you need, you can do the same. You only need to upgrade your contract. CKB environment stays the same. This way, you can also get all the nuances of new developments in the WebAssembly spec without affecting your blockchain implementation or without jeopardizing your security of your blockchain. We believe, so a lot of people see RISC-V versus WebAssembly as a competition. We don't believe this is a competition. We believe RISC-V is just one layer below WebAssembly, that you can use RISC-V instruction set to implement WebAssembly programs. And as I mentioned earlier, we believe a good blockchain virtual machine should also have distant cost model. As it turns out, for RISC-V, there's a very natural cost model because every single instruction running in the CPU has an associated cost, which is called cycles. It's only determined by the instruction you write. So the same instruction runs spend the same amount of cycle whenever it runs and wherever it runs. So we can just use that cycle directly as the runtime cost model for your program. This thing is made to scale, and it's also future-proof because it's defined by the underlying CPU. It's not defined by a workload. So if your program does more, it will naturally cost more cycles. If your program does less, it will be also consume less cycles. And the different thing is that since we are actually building on RISC-V, which is like a real minimal computer, we can just assign a single static memory space as the space you can work calling a CKB VM. Actually, in our current implementation, we set up the virtual machine memory limit as 4 megabytes. In this 4 megabytes memory space, you can do whatever you want. But what you cannot do is use anything that's beyond this 4 megabyte memory space. This thing gives you a fixed, bounded memory space, and you can be sure that your virtual machine instance can only consume this amount of memory. The security is guaranteed. And also, there's a lucky accident. We didn't design for this, but this turns out to be a very interesting use case. We're working to make CKB VM really fast. We're working to make sure that our standard can just use a software implementation, but it doesn't stop the problem. Doesn't stop the use case that you can use a real RISC-V CPU as a virtual machine in CKB. For normal use cases, this might not help a lot, but if you think about it, there are many exchanges and mining pools that might benefit from a higher TPS. So for them, they can just use the separate RISC-V CPUs, which guarantees the security because it's an isolated part from the main CPU, but it also runs very fast because you have a native hardware-based CPU here. So we believe that using RISC-V as a blockchain virtual machine is not about finding a hardware instruction set or finding a software instruction set. It's only about we need to find the right abstraction level we need for a blockchain VM. So that concludes my first part about building how do we design a blockchain VM that suits the needs for the future. The second part is about how we actually build this VM in real using Rust. First, there's some real numbers. We have devised CKB benchmark code written in C. We compile it to native code, which means the x86 code that can directly run on today's hardware. We also compile the same program into RISC-V. We also compile this program into WebAssembly, and we do analysis on the different runtimes spent by the same program in different environments. As you can see from this slide, our CKB VM has two modes. It has an old interpreter, it also has a fast JIT. For the interpreter mode, it's about 55 times the runtime of a native environment. For the JIT part, it's about 8 times the runtime of a native environment, which is actually within the same order of magnitude as a native environment. For our use case, this is more than enough. And what I want to compare here is that if you look at the WebAssembly implementation, it's also roughly the same level of performance. It's also roughly the same level of speed as our RISC-V program. You see there's two modes for the weather implementation. If you look at the pre-lift implementation, it's the same level of speed as our CKB VM in JIT mode. If you look at the LVM part, it might be slightly faster. But this gets more interesting if you look at the actual lines of code needed to implement each part. As Brian mentioned earlier, our CKB VM only contains about 8,000 lines of code. If you count the pre-lift part of the WebAssembly implementation, it's about 100,000 lines of code. I don't even want to count how many lines of code I needed for the LVM part of this to be completed. Although I know lines of code is only one part of the thing, it might not contribute to the big picture. But 8,000 lines of code versus 100,000 lines of code can tell you that we don't need very sophisticated compiler technology to make CKB VM fast. And chains, they tend to use an old, slow, and crappy interpreter, which doesn't match the speed of the fastest VM. This is like, I think. But with CKB VM, we have the same implementation, both fast has the latest WebAssembly implementation, and also secure enough to run in a production blockchain environment. And as I mentioned earlier, the speed, the main factor contributing to the fast speed of the CKB VM is about finding the right abstraction. With the right abstraction, we don't need to do a lot of code, we don't need to optimize everything, do a whole lot of different optimization or use sophisticated compiler technology to achieve the speed we have. And Rust really helps us a lot in this case because for the most of the part we can use Rust to write a code that's really maintainable and can maintain the code clarity of the code. But when we really need to extract every last bit of performance, we can just go directly into C code or even assembly code to achieve this. And as I mentioned earlier, in most cases Rust is awesome, but please do be aware there are certain parts that Rust is not so great about. The first thing we find out is that we typically write this thing which is an enum inside of another enum case, but the space consumption for this thing grows really quick. In our very initial version, to store a single RISC-V instruction, it takes about 48 bytes. 48 bytes. A single RISC-V instruction in its original encoding only takes 2 or 4 bytes. And when we parse it and put into the Rust structure, it takes about 48 bytes. This is going to put a lot of pressure on memories and their cache hierarchies. So what we have to do is that we turn this single enum thing into a 64-bit integer. We have to embed the data we want in a single byte of this 64-bit integer. This defeats the purpose, the beauty of the Rust enum type, but this is what we have to do because we want to speed. The second part is that we all know that Rust has this amazing pattern matching feature. It really simplifies your code and helps you maintain your code clarity. But the thing is, these things are not always so fast. So if you have an enum type whose subtype each contain a different size of value. So what you actually want from this PD function to do is that take a look at the type of the app and then jump directly into the code to execute the different part. But what instead is done in the assembly level is that it compares the value each 4 times. First time it compares if it's bar, second time it compares if it's best, third time it compares if it's a different thing. So in the worst case, if your enum has 4 different subtypes, your computer will really do 4 matches to see if the enum is of different type. This also contributes a lot of part in CKB VM in the original version that's slow. And even when we solve all these things, there are certain parts in the Rust compiler which is not so obvious. On the left side is a thing that's using an old for loop, which is like how you're writing things in C. On the right side, we have an iterator-based part, which is like that should be fast and help preserve code clarity, and which is written in the Rust way. But the reality is that the code on the right runs 3 times slower than the code on the right for a single change like this. So we have to revert the Rust way of doing things and go back to the plain C way of doing things. And at this stage, we have our first Rust-based interpreter, but it still runs slower than our standard. So we have to look elsewhere. So what we end up with is actually an old article written by Mike Paul, which is the creator of the Lua chip. What his ideas in this article is based like current C compilers and the Rust compiler, which doesn't exist back then but still holds here, is that they're only optimized for one type of layout. But if you're building for a virtual machine, you really want a different type of structures. And for this different type of structures, the current C compiler and Rust compiler won't help a lot. You have to really he suggests a different way to really handwritten assembly-based interpreter to make sure this speed up. To show a real example here, so this is what a Lua chip needs to run a single add instruction. You do a little count here, we have about 13 instructions. So it takes, in the assembly-based interpreter, it takes about 13 x86 instructions to run a logic add instruction. For comparison, a normal C-based interpreter usually need to take like hundreds or even thousands of x86 instructions to finish the same thing. So from a raw comparison, you can see that a assembly-based interpreter can really help you extract the speed, extract the performance you want, and make sure you optimize the thing well. And we basically do the same thing for CKB VM. So this is how CKB VM spans to run a single RISC-V add instruction. You can also see here we have 13 RISC-V x86 instructions for one RISC-V add instructions. You compare, so the ratio here is 13 versus 1 compared to a ROS-based implementation, which is usually like 1,000 versus 1. This brings us a huge speed up. But this actually is where I show the number of 50 times slower than the native version. But we didn't stop here. So if you look at all the assembly here, only the 4 assembly in the middle layer are actually doing work. Everything else is just overhead. So is there a way we can eliminate all this overhead and really only do the work we need? That's how our AOTG version is built. So how the AOTG works is that we take the RISC-V program and we compile it directly to x86 program. So in most cases, the VM can directly just run in the generated x86 assembly. It doesn't have to use the VM for any help. There are certain extreme cases where the generated assembly won't cover. We have to go back to the VM, but it only contributes like 1 or even 0.5% of the time. And the good thing about ROS is ROS has amazing foreign function interface that really helps a lot in our implementation. And we believe the best word to write a performant ROS program is actually a balanced one. So in 90% or even 80% of your case, you have a ROS program which is written to its high level maintainability and has a very good code clarity. But where you really need to push the last bit of performance out there, you can go directly into a C layer or a assembly layer to help you achieve that. This is a real stack gathered from our current program. You can see that our project has like 5,000 run lines of ROS code, 1,000 lines of C code, and also around 1,000 lines of assembly code. That's all you need to build something as performant and as complete as CKB VM. So as I mentioned earlier, we're not compiler expert. We only apply certain technologies, but we don't use like very sophisticated technology like the LVM case. But with the right abstraction, we can achieve the same amount of performance there. So we believe that software development here is mostly about finding the right abstraction. And for blockchain VM, we believe that Responseware is the perfect solution here. And that concludes my talk. I don't believe I have time for questions here, but I will stay here. If you have any questions, feel free to talk to me afterwards. Thank you.